Goes on from the Bernoulli random variable, but it actually says, let's imagine we were going to do this as an experiment where we did it over a lot of trials as we went. Okay, so you can see in the corner of the screen there's a little spinner, and it would be a blue or a white that you get. Okay, and this says, suppose X equals the number of blues which result from spinning this spinner once. Okay, now that seems a little bit strange, but you can imagine if you kept spinning it, every time you would record, okay, did I get blue, did I not? Did I get blue, did I get not? But you would need to know how many trials you were going to do it for. So maybe if I said to you, you're going to spin that spinner 100 times, how many blues do you think you would get? 75, Henry. Excellent. Yes. Okay, so the maths behind most of this stuff initially is nothing dramatic. Okay, but we would say that blue was a success, white was a failure. The probability of a success is 3/4. But if we did it 100 times, then we can use this Bernoulli random variable and say we can get a value that we actually get. Okay, so we would expect that we would get 75 lots of the blue. Okay, now if I did it another 100 times, I might get 70. If I did it another 100 times, I might get 83. If I did another 100 times, I get another value. And you could keep doing that for the 100 spins and see what you got. And you could imagine that over time, you would build up a bit of a spread of the values that you possibly got. Okay, but we call this a binomial experiment because there are only two outcomes. Okay, importantly, and before the previous, when we're looking at the Bernoulli, there was a question about state whether or not it was a Bernoulli variable. You're unlikely to get that as a test question, but this idea comes up quite regularly, and it's about whether or not some experiment could be considered a binomial experiment. And there are two things that you're looking for. One, we need to know how many times the event or the trials are going to be done. Okay, and we would say that that is n. Okay, and that would need to be set already. We can't sort of change that as we go. It's not like, we'll play, rock, paper, scissors, and then when the person loses, we'll say, oh no, it's actually best of three, or whatever. It's something you have to set beforehand. Okay, the probability of a success and a failure, in fact, it's more than two things. The probability of a success and hence the failure has to be the same every single time. Obviously, that can't vary. We can't say, I'm going to change my spinner now and do a different one for the same one. It can be obvious. Each event has to be independent of the previous one. So it's not like when you have, the 7 reds and 3 blues in a container and you take one out. If you don't put it back in again, the next time you pick, that probability has changed of what you're going to get. So it can't be considered that. However, we can have examples where if you had like 7 million of them in a container of one colour and 3 million of another colour, and you took one out, the probability will change that small amount that you might say, well, the probability change is negligible. So for this small experiment, we can still call it binomial. It approximates it well enough. Okay, but they should be independent. So they're the things that are important for this to be true. Okay, and I think they're fairly obvious things anyway. So we will at times use tree diagrams, not too big, they get messy. Okay, but this is how we're going to use to show how we can avoid tree diagrams, I suppose. So this is a tree diagram of the things that could happen from that spinner. Okay, so we could get a blue or we could get a white in that first spin. You can see that on the pathways, the probabilities have been written. Okay, so the probability of getting a blue is 3/4. So we would imagine most of the time we're going to go up that pathway, or 3/4 of the time we're going to go up that pathway. And then that same probability sits as we go through the paths. So what we've got here is all of the actual pathways that can occur for this event if we were going to do it for 3 spins. Okay, so we're going to do 3 trials, okay, and we could get 0 that are blue. We would imagine that's very unlikely because that means we had to get a white, a white, a white, and there's only a 25% chance of getting white first. Okay, we could get 1 blue, 2 white, we could get 2 blue, 1 white, or we could get 3 blues. Okay, the first thing that I want you to come or see out of this is how many different ways could we get none are blue? There's only one pathway that gets white, white, white. So I'm just going to put that there. There's one pathway for that to occur. Okay. How many pathways are blue, 1 blue and 2 white? Well, they're the ones that have got the ticks because of where this example came from. So you can see go up to blue, then white, white, or go down to white, then blue, white, or go down to white, then white, blue. So there's 3 possible outcomes. Okay, or 3, not outcomes, 3 possible ways that that could occur. Okay, the 2 blue, 1 white. Okay, so we're going to have 2 blue, 1 white is going to be to this pathway here. Okay, this pathway here and this pathway here. 3 of them, and there is only one way that you can get 3 blues. Okay, following the top pathway all the way along. Okay, so 1, 3, 3, and 1. Okay, if I went one step further, I'm not going to draw it all in there, but if I went one step further and said, oops, I need that to be a whole lot bigger. Then I said, let's do it for 4 spins rather than for 3 spins. Okay, then you would have from here, you can see quite a lot of different pathways that would occur. Okay, lots of different ways that would happen. Now, the outcome would also include, in this list over on this side over here, we would also include 2 blues, 2 whites, as well as having the 1 blue and 3 whites and 3 whites and 1 blue. Okay, so we're going to have one more spot that could occur. All right, and I'm going to tell you that without actually going through it, you can go through it yourself, but it's one possible, 4, 6, 4, and 1. Okay, so is anyone following? I mean, some of you are following what pattern I'm coming up with here. All right, yeah, remember that special triangle? Okay, so you have that, love this triangle. It's extremely helpful. In a second you'll see why. But from last year, do you know how to come up with the numbers that are in Pascal's triangle without having to actually do Pascal's triangle? So what I mean is, yeah, you can use combinations. What I mean is, if I said to you, I need you to go down and work out what value sits there, all right, you can tell me that it's going to be 15 because you add the 5 and the 10 there, but can you tell me what value sits there if you do not draw Pascal's triangle? Which, to be honest, if it was only that value, it's probably nearly quicker to draw Pascal's triangle because it takes no time at all. But if it was down another 10 rows, then it's going to take you a long time to draw that and you don't want to do it. Okay, so we use combinations to be able to get there. What's it really doing? It's telling us, in this case, Pascal's triangle has other uses as well, but in this case, we can use it to tell us how many different ways can that outcome occur. And that's really important, okay? Because each time that outcome occurs on our binomial experiment, any pathway that we take, okay, has a probability. But any pathway that gives us the same outcome must have the same probability. What do I mean by that? If I just delete this stuff here and go back to what we've got at the start, if we look at the one that they've got ticks for, we've got blue, white, white along that way. This one here is white, blue, white, and this one is white, white, blue. There are 3 different ways. That's the same outcome. In our experiment, that's the same outcome because our outcome is asking us, how many blues did we get? Well, that's the outcomes that are possible to give us 1 blue. Okay? The probability of all of those paths must be equal to a blue, which is 3/4, times by a white, which is 1/4, times by a white, which is 1/4. They're in different order, but it doesn't matter which order you multiply things. Okay, so that's going to tell us if we did this pathway here, okay, it's going to be what, 3 over 464. Okay, that is the probability of getting that exact pathway, but we have 3 pathways that have the same probability, so we're going to multiply that by 3. Okay, so how are we going to use that? What's the point of it? You may have seen something that looks a little bit like this before, maybe not written exactly like that, but this is effectively binomial expansion, okay, which hopefully you did a little bit of before. Okay, what this is saying very mathematically, and we'll look at an example which will help better in a second, but it's saying very mathematically that the probability of the success, the x being the success is equal to k, is going to be equal to this notation. When you did combinations last year, did you use the notation like that? Yeah, I much prefer to, like if I'm doing it, I would probably write it as being C, and you either have it like that, or sometimes you see it like that, okay, for combination. The only reason is it starts to look a bit vector-like when you write it in that notation that's up there, okay? But that's just saying the combination. What it's saying is, if I have n trials and I get k successes for it, okay? So in our previous question, this one here, where we're talking about getting 1 success of a blue out of 3 trials, what we're saying is 3 trials getting 1 success. Okay, now I'd have to remind myself on your calculators where you can do combinations. It's in there somewhere. You'll need to know where it is. We'll find it in a bit, but find where you can put combinations in, because you don't want to have to do them by hand. We're not going to use factorial notation to do it by hand. You just use your calculator to get the value. Okay, I already know that has to be equal to 3. If there's 3 trials and your probability of getting 1 success, that success could happen on the first trial, second trial, or the third trial. Okay, so there are 3 ways, but if it's bigger, we won't remember it. And then what we're going to do is say, well, it's the probability, okay, of, so this second part here, it's the probability of k, which is a getting that many successes. Okay, and we multiply that by, the probability of a success times by 1, not times by 1, to the power 1. Okay, so our probability of a success was 3/4. So let's actually put it in. We're going to have 3, 1, C, or the 3 and 1 afterwards, doesn't really matter. And we're going to times that by 3/4, which was the probability of a success, and that's to the power 1. And we're going to times that by the probability of a failure, which is 1 take P, or 1/4. And that's the power n take k. Effectively, it's going to be the number of trials take away the number of successes. So it's going to be 2. Okay. Now, ultimately, that just equals 3 times by 3/4 times by 1/4, which is what we did before. Okay, so that's the mathematical way of doing it. All right. We're going to see, that the calculator can do a lot of this work for us. We'll do that in the next lesson probably. But how we can skip doing a whole lot of work. So let's look at their example. Okay. And their example is important because it does everything, but it shows perhaps you don't need to do everything when you're trying to solve something. And you're not going to get a question in the test or an exam where you have to expand the whole lot. But what you would need to do is find which part do I actually really need. So this has just got a binomial expansion at the start. It's just saying expand 9/10 and plus 1/10 to the power 5. Okay, but let's sort of forget it from that point of view and just think about part B. So an archer has 90% chance of hitting a target with each arrow. If 5 arrows are fired, determine the chance of hitting the target twice only. In the first time, twice only, and the second one at most 3 times. Okay, let's not look at that expansion as being the expansion of binomial. Let's think about that expansion as being, okay, what's actually happened? So in B, all the bits that are underlined in the red there are the parts that are important. So we've got a probability of a success, P. So I should write that. P is equal to 9/10. 1 take P equals 1/10. Okay, so that's our probability of a success and a probability of a failure. Okay, when we expand it out, the first value that you get, if you do it in the sort of the correct order, would be to say we have 0 successes. Okay, remember the probability of X equaling 0. So 0 successes means fail, 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 fail. It is just going to be 1/10 to the power 5, because 1/10 times 1/10 times 1/10, 5 times. Okay? There is only one possible way that can come out. Okay? So what's not really written on here that I think is important is to say that would be the combination of 5 attempts or 5 trials and having 0 successes. If you put that into the calculator, the value comes out as 1. It tells you there's only one way that can possibly happen. Okay. Here, the second one, where you've got 1 hit, so what's the probability of getting 1 success? You get 1 hit and 4 misses. Okay. So the 5 that's out the front, all right, that comes from Pascal's triangle, or better still, it's a lot of room. It's 5 trials. Oops, that 5 is too big. 5 trials, 1 success. Okay, so you calculate, if you know that's the one you need to do that. Well, there is going to be 5 different ways that can occur. Okay, so that 5 is at the front, that's where the 5 comes from. It's where the 10 comes from here, it's where this 10 comes from here. That's just saying what's the combination of, how many different combinations are there of 5 trials and getting 2 successes. 5 trials getting 3 successes. Okay, that multiplier is there. The other part for the expansion is to follow through and say, okay, how does the indices or the powers work here and here and here and here, etc. Okay, effectively you can think of it mathematically like the formula that was given on the previous slide, or you can just go, right, if it's 1 hit and 4 misses, then I'm going to put my indice as 1 hit and 4 misses. Okay, as long as my probabilities are in the right spot. Okay, 2 hits, 3 misses, etc. Okay, and you can see it breaks down into certain parts. Now, breaking it down to those certain parts is really useful because the question only says, in the first bit is what's the probability it hits twice only. So you get 2 successes. Okay? All you need is that part there. So you wouldn't need to do the whole expansion. You'd just do that one bit. You'd say, right, I need 2 hits. So I need the combination, the multiplier at the front is going to be the combination of 5 trials, 2 successes. Put that into the calculator, comes out as 10. Okay? And then it's going to be 9/10 to the power 2 hits and 1/10 to the power 3 misses. Okay, and we can come out with a result without having to do all of this expansion here. Okay, the second part there is the probability of hits at most 3 times. Now that means you have to do more work because it's saying, okay, what's the probability it hits at most 3 times? Okay, that means it can hit 3 times, it can hit 2 times, it can hit 1 time, it could hit 0 times. So it's adding all of those up. Or I would say, hang on, if that's all of these ones here, okay, the probability of this whole thing here has to add up to 1 because they're the only things that can happen. If you have 5 trials, they're the only things that can happen. Therefore, I could just add up those and do 1 take that value. Okay, so I could do it more quickly if I think carefully about the question. That's really important. If that had said the probability of hits at most 4 times, then it would be silly, all right, to do all of them if I just have to do 1 take that value there. Okay. So lastly, let's have a quick look at this question and see if we can answer these ones together. I probably won't use the calculator to do it. We won't expand that. Okay, but it says in New Zealand in 1946, this is fairly random, there are 2 different coins of the value 1 florin. Okay. These were normal Kiwis and flatback Kiwis in the ratio of 3:1. From a very large batch of these, 5 were selected at random with replacement. So you'd take one and put it back. They've said with replacement because what that does is it keeps the probabilities the same each time. Okay, so if I wanted to find the probabilities that they were all flatbacks, if 2 were flatbacks, I only want 2. So if I said that flatbacks are by the looks of this question, these were normal Kiwis and flatback Kiwis in a ratio of 3:1. So 1 in every 4 is a flatback. And it looks like, if I look at the question in part A, the way they've expanded it, to me, looks like they've said that a success is getting the 3/4 one, the normal Kiwi, but it says 2 are flatbacks. There's absolutely nothing in the question that tells you have to say this is a success or a failure, as long as you just say, well, how am I going to set it out? Because you'll get the same answer in the end. Okay, so if 2 were flatbacks, and I want to think about flatbacks, okay, then my success is a 1/4, okay, and my failure is a 3/4. Now you could do it the other way, doesn't really matter. In fact, in part 2 and 3 it swaps anyway. So if 2 were flatbacks, the first thing is the multiplier out the front. How many different ways can that happen? There were, how many? 5 were selected. And we want 2 of them to be successful. And we're going to then multiply that, okay, by our probability of the flatbacks as the success. Okay, is 1/4, and I want 2 of them to be that, and 3/4, they must be 3. Okay, and then you put that into your calculator, and that'll be your answer. All right. Part 2, at least 3 were flatbacks. Okay, so at least 3 were. Okay, that means that 3 or 4 or 5 were. Okay, when you're in the middle like that, there's not a lot you can do except for saying, well, I want 3. Okay, so 3 were, that means that 2 weren't, plus I want 4 successes in this case, so 1/4, 4 and 3/4 to power 1, and the last one could have been all 5 were the flatbacks, so it would be 5, and I've got 5 times by 1/4 to the power 5. It is times by 3/4 to the power 0, but 3/4 to the power 0 is just 1, so we can drop that off. Okay, so you'd need to add up all of those. Okay, so add those 3 together. And then it says at most 3 were normal kiwis. All right, now if you think about that, at most were the normal ones. Okay, at most 3 of them were. So 0 could have been normal, 1 could have been normal, 2 could have been normal, or 3 could have been normal kiwis. So if I was going to do that one to make my life quicker, I'd try and say, well, the opposite to that would be to say, well, 4 were normal or 5 were normal are the ones I'm not interested in. So I would say 1, take. And if we're talking about normal now, I might think for this part, I'm just going to make normal the success. It doesn't actually really matter. But if I think of normal as being success, I want 1 take 4 successes. So that's going to be 5 with 4 successes. The only difference between this and the previous 2 is to say now my success is the 3/4, and that's 4 successes. Okay, it's 1 take that plus the 5 successes, 3/4 to the power 5. Now, certainly you could have just added the other ones up. You could have done 0 normals, 1 normal, 2 normal, and 3 normals. But then you'd have 4 bits that you have to put into your calculators. It's going to save you a step. Okay. That is what I want you to have a go at, doing some of these ones using the calculator to find out those combinations rather than using Pascal's triangle. There is no reason, I'm not sure looking at the questions, but there's no reason why they couldn't have a question that had, say, like 12 trials. And you certainly don't want to have to write Pascal's triangle down 12 lines to get to the possible outcomes for it. Okay, you just use your combination button.